Smart Cerebrum Private Limited is a team of academicians and experts who are into education field since decades. We are proud to be associated with more than 1,500 institutions across the country. We are into academic consultation, teacher training, student training, communicative English, Vedic mathematics, subject-specific training, content development, and many more. Smart Learning is a service-oriented social initiative from Smart Cerebrum Private Limited, wherein subject-specific experts will be conducting online sessions for the student community at large. Please subscribe to our YouTube channel for constant updates about upcoming sessions and topics. All the sessions will be related to the syllabus and curriculum.
We welcome Dr. Balaji Rao sir and all our viewers for today's session. As this session is for grade 10 chemistry, acids, bases and salts part 4. Please type the queries on the YouTube channel. We will be taking up the queries before the session ends. We welcome you sir.
Thank you.
Please continue sir.
Thank you very much. Very good afternoon to all of you. Today will be the concluding part of this topic on acids, bases and salts, after which we will be giving ourselves an introduction about metals and non-metals. That will be a fairly lengthy topic to deal with, so it will take a while for us to go through those contents as well. But to begin with, as we always do, let us try to go back, review what we have done in the previous session, so that will give us a small impetus to go forward. The last class when we had met, that was in the previous Friday, we had talked about this chloralkali process. In chloralkali process, if you recall, we had taken brine, that was sodium chloride solution, that was electrolyzed. When brine was electrolyzed, I'm not going back into the picture because you've already seen the picture once and it is available as in a better form in your textbooks as well. So we will just try to keep, if you have a textbook, keep this in front of you, open that diagram and see what we are going to discuss. Whether it comes up or not, let us see. So in chloralkali process, as the name suggests, there are 2-3 things that are being produced. One is chlorine, obviously. The other is alkali. Alkali is sodium hydroxide. And the other byproduct of this process would be hydrogen, which we have already seen. So in chloralkali process, brine is electrolyzed, as I said. When it is electrolyzed, what happens? Chlorine gas is liberated. First step would be obviously ionization of sodium chloride. Sodium chloride ionizes into sodium plus and chloride minus ions, both aqueous. Then at the anode, that is a positive electrode, chloride ions migrate, they get discharged, they get oxidized into chlorine gas, which is separately collected. And at the cathode, 2 things happen. One is hydrogen ions will move towards the cathode, get converted into hydrogen gas, which is liberated, and near the cathodic surface, the sodium ions and the hydroxyl ions from water. You might ask, where is the H plus and OH minus coming from? They are coming from water, which is slightly ionized. So the OH minus ions from water would have reacted with or will react with Na plus, giving rise to sodium hydroxide solution, which is tapped off. Now looking at why is this process so commercially very, very important? We know that hydrogen is a very important commercial chemical, and today, in today's context, hydrogen is a very, very, very important, as I said, commercial substance, because today we are talking about cars which are going to be run on water. People are talking about these fuel cells where hydrogen gas and oxygen gas are made to combine forming water, and during the process, a lot of energy is liberated that is used to make the car run, automobiles run. So this is one important commercial use of hydrogen as it is right now. This is a hot phase of hydrogen. Then, of course, it is used in making what is called as vanaspati, or what we call as dalda. It could be called margarine or margarine, as it's a proper noun, can be pronounced anyway. Margarine or margarine is nothing but oil which has been converted into an edible fat. Now, all of us know that conventionally, only few oil seeds are used for preparation of food. If you come to the place where we all live, that is Karnataka, predominantly we use groundnut oil. But of course, of late, for the past couple of decades or maybe more, we have switched over to something called sunflower oil, which is again a substitute for, supposed to be a substitute for groundnut oil. Then we have, if you go up the north, you have oils like mustard seed oil, etc. Then there are some oils which are not totally edible. You cannot eat, for example, castor oil. I don't think you've ever tried doing it. If you do that, you will have a severe bout of loose motions. It's used as a very, very big, in a big way, a laxative. But if I have produced large quantity of those kinds of oils which are not edible, if I want them to be converted into something which is edible, then I can keep this oil heated to about 180 degrees centigrade, put powdered nickel into this, and pass hydrogen gas under pressure. When I cool this whole mixture, I'll find that the oil would have been converted into an edible fat. This edible fat is commercially sold as dalda, etc. We know there are so many names that are given to it. And incidentally, this is also called as a trans fat, because you will learn this a little later, what we mean by trans fat. All these oils contain a number of double bonds, and hydrogen is always added across a double bond. And when it does so, it happens to be in the trans position. That means across opposite of a double bond. More information you will be getting as you go to higher classes. This so-called trans fat is not good for health, so people advise you not to consume too much of the products sold in these bakeries. Any confectionery that is prepared would invariably have confectionery in the sense like a bread or a bun or whatever you have. All these foodstuffs, they do contain sufficiently large quantities of trans fat, which are not good for the heart, they say, in the long run, of course. Then, of course, hydrogen is used in manufacture of ammonia. Ammonia is a commercially, once again, very important compound for us. It's there in nature. Ammonia is there in nature in the form of its salts, but that quantity of ammonia may not be sufficient to make a fertilizer or to make large quantities of fertilizers. So ammonia needs to be manufactured, and there is a process called the Haber's process. You will again learn lot about it as you go higher. Then this ammonia is manufactured from, of course, starting hydrogen. Then from ammonia, the sequence goes on: ammonium chloride, ammonium sulphate, ammonium phosphate, etc., etc. So for all of them, hydrogen happens to be an important starting material. So hydrogen is commercially a very important gas for us. All right. What about chlorine? All of us know that chlorine is used in disinfecting drinking water, because whatever microbes that are present in water can be killed instantaneously by chlorine. It is used to treat drinking water. It is used to clean the swimming pools, to see that the water is not, in any way, it doesn't contain any of these microbial things. Then, of course, it is used in making of polyvinyl chloride. Polyvinyl chloride, we know PVC is a very important commercial plastic for us. There are different grades of PVCs. We will not go into the details of this at this point of time. Then it is used in making chlorofluorocarbons. We know about chlorofluorocarbons, so-called freons. These freons have been used, even today they're being used in the compressors of refrigerators. And there's a lot of hue and cry about the ozone. By the way, yesterday was ozone day. As I remember, ozone layer is supposed to be being depleted because of excessive liberation of CFCs into the atmosphere. So beginning from the humble refrigerator to the massive air conditioners that are there in huge airports, a lot of CFCs are being spewed, and these are supposed to be causing holes in the ozone layer, which is actually acting as a protection against ultraviolet radiation from the cosmos. So this is one set of very few things I've mentioned about here. Of course, incidentally, chlorine is used to make chlorinated rubber paint. That's again one thought randomly that came up. This chlorinated rubber paint is what you find on the roads, to mark the zebra crossing or to mark, these directions, etc., on the road, on the asphalted road. So chlorinated rubber is used it used to be, and continues to be used as a material for making these kinds of paints. Then together, hydrogen and chlorine, they give us another very, very important substance called hydrogen chloride, or fondly as we call hydrochloric acid, the aqueous solution. Hydrochloric acid is not only a lab reagent, as we all know it is used as a lab reagent. It is also used in pickling or cleaning of steel. Steel, we know, is made up of iron and carbon. Of course, small quantities of chromium is there, some amount of manganese is there. Different metals are also present. Carbon is there, of course, carbon, iron, some amount of manganese. These are the principal components of mild steel. But then this steel tends to corrode, means it undergoes corrosion. We have already mentioned about this word corrosion. We'll be dealing a little more of this in this coming chapter, which we will be talking about in terms of metals and non-metals. So here what we find, to remove that mill-scale corrosion, as we call it, thick formation of corrosion, the metal sheet is dipped in hydrochloric acid solution. We call this as pickling, acid pickling, and the entire rust is removed, washed off. Then hydrogen chloride or hydrochloric acid is used to make ammonium chloride, which is an important, as I said, fertilizer. And if you have noticed, I think I did mention this to you last week as well, any tablet that you consume, any medicine that you consume, if it is in the solid form, or even if it is an injectable form, please note, if at all you touch wood, let us not go to a doctor at this point of time. In case of any small emergency, health emergency, if you go to a doctor, if the doctor gives you a medicine, a tablet, look for the strip in which the tablet is placed. You will find that there will be some word related to hydrochloride. So all medicines that we consume should be soluble in water, only then the body will accept it. Otherwise, it will be rejected straight away. It will have no effect. So all hydrochlorides, in fact, organic hydrochlorides too, they're all water soluble. So to convert any given medicine or a medicine into a soluble form, this hydrochloride has to be prepared, and there we use hydrochloric acid. So hydrochloric acid is used to make a number of important medicines as well. And you'll be surprised, a number of so-called beauty cosmetic creams, cosmetic lotions, they all do contain hydrochloric acid in a different form, not necessarily concentrated hydrochloric acid itself, but they're used to make hydrochlorides, which are again water soluble, which can be washed off, and so on and so forth. Then coming to chlorine per se. If you look at chlorine's uses, it is used to make bleaches, to bleach clothes, and it is used for bleaching fabrics and so on and so forth. So a number of uses we have seen for hydrogen, chlorine, and of course hydrochloric acid. These are potential 1 mark questions for me, maybe 2 marks as well, because there are some questions which are what we call as bonus questions, which are so simple and straightforward that without thinking much, you can write the answers and get marks to score more marks. So there, these are the type of questions that might be given. Write any 4 uses of maybe chlorine, or maybe hydrogen, maybe hydrochloric acid, and so on and so forth. These are all simple questions which are aimed at knowing how much you remember. Now we come to another very important substance which is commonly used at home. Generally, there's no household which does not use this. It is called the bleaching powder. All of us know bleaching powder because it is very ubiquitous. It is present everywhere. The chlorine, how do we make this bleaching powder? Chlorine obtained from electrolysis of brine is passed over heated slaked lime. Slaked lime, dry slaked lime. Slaked lime is calcium hydroxide. Let us see how the reaction takes place. We have this calcium oxychloride, as we now call it, CaOCl2 is called calcium oxychloride. Calcium oxychloride is what we call as bleaching powder. We all know where it is used. To begin with, it is used to bleach cotton. Cotton, we know, has a substance called lignin that binds the cellulose together. And over a period of time, the cotton begins to yellow. It begins to become yellowish. So when it is, in fact, made, cotton fabric is made, it is not pure white. So to make it more attractive, this is bleached. So when it is bleached, for bleaching it, we use a solution of a substance, no, not solution, it is actually a suspension of this bleaching powder, and then this cotton becomes bright and white. It is used in, bleaching powder is used in bleaching of wood pulp. I mentioned to you about cotton. The same thing goes with in the case of wood as well. Wood pulp that is used in paper industry. Because you know, again, paper is made from wood. And of course, don't think that all the paper that we use is made by starting from wood, because most of the paper that we use today is recycled. The old notebooks that you have disposed of, the paper that has come to you in some form, large quantities of paper that is being wasted unnecessarily, that paper is pulped again and again. It is made back into your writing paper. And because the paper is very, very, very porous, we add substances like aluminum oxide to this, and we give what is called glazing. The paper is glazed so that it does not absorb ink. So during the process of making of paper, to see that the paper does not become yellow, it is bleached with using calcium oxychloride or calcium hypochlorite or bleaching powder. Then it is used in as an oxidizing agent in some organic reactions. We will not go into the details of it if at all you are very interested, because this is a point where I want people to get excited about knowing how things work. As I have been mentioning this is probably third or fourth time I have mentioned this to you. You people are in a very lucky generation where information is at your fingertips. All you need is open your phone, Google, and you get information. But again, be cautious about what information you get, because some of the information may not be 100% true. So check the authenticity and then proceed. Then it is used to make water fit for drinking. That is again in disinfecting of drinking water. So bleaching powder is used, as we see, to bleach cotton, to bleach paper, and to oxidize as an oxidizing agent in organic reactions. And of course, it is used for disinfecting drinking water. It is most commonplace uses your swimming pool, again, as we know. Now, having seen this bleaching powder, again, you should be, I'm sure you know this, that bleaching powder comes to you in a plastic packet which is doubly sealed. And if you expose it for some time, you see that it becomes sticky. That is because calcium hydroxide is hygroscopic. It absorbs moisture, and that is why it makes that bleaching powder sticky. All right. Now we go to the next commercially important compound for us. I'm going a little fast today because two reasons. One is we'll be ending with this topic, and number two, we will be taking up something which is a little more interesting than what we have been seeing so far. Because we'll be going in the next chapter, believe me, we will be going into inside the atoms virtually. We're going to see how electrons get transferred, etc., etc. That is, again, I'm just giving you a small brief into what we will be doing. So in that, I am going through a little faster. And in case it is very fast, please put it on your chat box so that I can get the response to slow down whenever needed. All right. So we come to baking soda. Baking soda, we know, is again a commonplace substance for me. There is virtually no household worth its name which does not use baking soda, especially during weather like this, where you have chilly evenings. Uh, Naturally, you will be tempted to eat uh, deep fried pakoras and vadas, whatever you want to. And you definitely would pester your mother to prepare something. And during preparation of pakoras, to see that they become that crispy, a certain amount of baking soda is added. Baking soda is chemically NaHCO3 sodium bicarbonate or sodium hydrogen carbonate. So we write baking soda here. It is sodium hydrogen carbonate or sodium bicarbonate. Now, sodium bicarbonate is prepared starting from sodium chloride, carbon dioxide, and ammonia. This you will be seeing again, these three raw materials, you will be seeing again in the case of sodium carbonate too. Sodium carbonate, we'll be talking about this as washing soda, is made by the same procedure as sodium bicarbonate. Incidentally, sodium bicarbonate is produced during the reaction or during the formation of sodium carbonate itself. Let us see how the reaction takes place We start with sodium chloride solution. Into sodium chloride, we pass carbon dioxide, and we see that this is treated with, of course, a solution is there, plus ammonia gas is passed. When this happens, we get two substances, ammonium chloride and sodium bicarbonate. Now, both ammonium chloride and sodium bicarbonate are soluble in water, but when we cool this mixture, the sodium bicarbonate is less soluble than ammonium chloride, and therefore sodium bicarbonate comes out as a precipitate. Ammonium chloride is highly soluble in water. Even at a low temperature, ammonium chloride remains in solution, so sodium bicarbonate precipitates out. This is taken out and it is filtered and it is used. Now, sodium bicarbonate is a salt of, as you can see, a strong base and a weak acid. It is a salt of sodium hydroxide and H2CO3, carbonic acid. We have already mentioned this name earlier. Now, because of this, when it is dissolved in water, it will give me sodium hydroxide and carbonic acid. And because sodium hydroxide is a strong base, that means it undergoes complete ionization. It produces larger number of hydroxyl ions compared to the number of hydrogen ions produced from the weak carbonic acid. Therefore, the solution will be slightly basic in nature. Okay. Now then, sodium bicarbonate is, if it is heated, what happens? Let us see. If I heat sodium bicarbonate, it will give me sodium carbonate. Let me see how it happens. Now, this sodium bicarbonate is easily converted into sodium carbonate. This is what I was talking about. This is the intermediate process during the preparation or manufacture of sodium carbonate, which we'll be seeing later. Coming to uses, it is used to, of course, as the name suggests, it is used to make baking powder, and it is used baking powder itself. What is baking powder per se? Baking powder is a mixture of sodium bicarbonate and tartaric acid. Tartaric acid is C4H6O6. It is a dibasic acid. We will not go into the details of the structure of this. It is not needed. It is called tartaric acid because it is obtained from tartar, which is a sour substance. It's a sour substance which is also present incidentally in your tamarind. In tamarind, you do find certain amount of tartaric acid present. So this tartaric acid is used along with sodium bicarbonate, and this mixture is what we call as baking soda. Now, how does this work? When we put sodium bicarbonate into an acidic solution, that is your tartaric acid itself, when we put sodium bicarbonate that is present in the baking soda into a solution containing an acid, that is your H plus present in from tartaric acid, this will give me carbon dioxide, water, and it will give me the sodium salt of tartaric acid, sodium tartarate. This H plus, as I said, is from tartaric acid. Now, this carbon dioxide rises through the dough and it will make it fluffy. In fact, uh, during winter seasons, it so happens that if somebody wants to prepare dosa or idli, the dough will not rise. So to make it rise, a small amount of baking soda is added, or like baking powder is added. If you add it, what happens? The carbon dioxide produced will see that the dough rises, and the material that is prepared out of it will be fluffy, etc. Now, sodium bicarbonate, coming back to this, is an ingredient of many antacids. Antacids, you have already talked about this. These are substances used to alleviate excess acid pain in the stomach. And it is used in soda acid fire extinguishers. Now it is not, you cannot see this, but when and as the cinema theaters open, you find that along the walls of these cinema theaters, you have big cones in a red, which will be triangular cones, and it'll be written as fire, and you're supposed to hit it down and allow the gas to be formed coming out, and it's a foam, that the foam extinguishes fire, and so on and so forth. So far nothing is happening, so leave it for the moment. So coming to washing soda, the next compound in question, this is sodium carbonate, and in its crystallized form, it is sodium carbonate decahydrate. That is washing soda, as we call it, is sodium carbonate decahydrate. We'll be talking about this hydrate a little later, probably in the 5 minutes from now. The sodium carbonate is obtained from the same raw materials which we used for making sodium bicarbonate, and we saw how sodium bicarbonate is converted to sodium carbonate. When it is crystallized, it gives me a compound of this composition, Na2CO3.10H2. Now, sodium carbonate is an important compound for me because it's used to make glass. The glass that we use people use for making window panes, right from window panes to most of the test tubes that we use in the laboratory, a lot of glass equipment, it is all called soda glass. Soda glass is sodium silicate, which is got from fusing this sodium carbonate with sand, that is silica. Now, this sodium carbonate is used to make glass, as you can see. It is used to make soap. Now, talking about soaps, it's an interesting small snippet that I want to share with you. You will be surprised that most of the soaps that you use, it could be any soap worth its name, is basically got by passing or by heating this sodium hydroxide or sodium carbonate with an oil or a fat. There are certain controversial points which you don't want to touch upon, so I'll leave it at that. It's for your imagination to, go higher and see what I have meant by this. But then sodium carbonate is used to make the soaps. And in soaps, how do you know whether a soap is going to last long or not? On any soap, there is something on the cover, wrapper, what is written as TFM. It is called total fat moiety. The higher this TFM, the softer is the soap. Because I was tempted to use this word because recently I just saw a couple of days ago on the television somebody advertising for a soap with 72% TFM and it's supposed to be very good. Nonsense. TFM makes it more soft. That is all. It becomes easy to, it just becomes too soft so that you can't handle it further. So soap with a higher TFM will dissolve faster in water, not dissolve, disperse in water faster, and that is all it does. Okay, so to make soap, to make paper, to make borax sodium borate, and it is used for cleaning agent in some cases, and it is used for removing permanent hardness in water. Sodium carbonate is used to remove permanent hardness. All of us know that the water is of two types, soft water and hard water. And soft water lathers easily with soap, whereas hard water does not easily lather with soap. So to make the hard water become soft, it is treated with sodium carbonate solution. Now a question comes to the mind. Are all these crystals of salts really, are they dry? What do I mean by saying dry? The answer to the question is somewhere up there. Let us take, of course, this I've already again mentioned. This is a repetition of what I'm saying. Most of the words will be repetitions. I used a word called copper sulphate, which I called as Mailututta, if you remember long back. Copper sulphate is naturally occurring in the form of its pentahydrate. Pentahydrate means it has 5 molecules of water associated. So CuSO4 dot 5H2O, it's a beautiful blue crystal. It's a beautiful blue crystal, and it's a lovely color, by the way. If you heat this, it becomes CuSO4 losing the water that is present. You can do this experiment. It's very easy to perform. All you need is one basic test tube and probably about a gram or two of soap of copper sulfate crystals. Heat it over a flame for a few seconds. You find that on the cooler part of the test tube, you will find deposition of water vapor. This water vapor is coming from this CuSO4.5H2O. This 5H2O that is associated with copper sulfate or 2 moles of water associated with calcium sulfate or 10 moles of water associated with sodium carbonate. These are called water of crystallization, or we can call this as water of hydration. If you don't like the word water, simply call it as lattice water. There are 3 names that I have given you here. These molecules of water associated with certain salts when they are formed, like in the case of copper sulfate pentahydrate, calcium sulfate dihydrate, sodium carbonate decahydrate, or ferrous sulfate hexahydrate, any of them, if you look at it, during the crystal formation, during the formation of the molecule in nature, in its crystalline form, these water molecules become an integral part of this. Therefore, they are also called as lattice water. Now, if you, this is a, these are molecules which are loosely bound. So if you heat it, this water gets removed. That is how copper sulfate became a blue solid, blue powder, blue crystal became a white powder. Now, question is, can we reverse it? Yes. If we take copper sulfate anhydrous white powder and we add water to this, a few droplets of water, it will give you back your blue copper sulfate. If you take sodium carbonate decahydrate, heat it strongly, you get Na2CO3, which is called soda ash. Again add water, recrystallize, you will get back your washing soda. You start with the gypsum, heat it very strongly, get anhydrous calcium sulfate, cool it, add water, allow this to again settle down, crystallize, it will give back your gypsum. So this water of hydration can be reversibly, added to the molecule. Now that gives me a lead into what we call as plaster of Paris. Plaster of Paris is a very commonly heard name. Uh, we find this people, sports people for that matter, or even anyone in general. If in case we trip and fall, or in case there is a crash somewhere, the bones might get cracked. If the impact is very high, the bones might get cracked, and we know it is x-rayed and then the crack is identified. And what the doctor does is he or she puts a cast over that particular part. We have seen people carrying a white cast over their arm or leg wherever it has had a fracture. Now, what is this made up of? This is made up of what we are going to talk about as plaster of Paris. What is plaster of Paris? If you heat gypsum to 373 Kelvin, that is about 100 degrees centigrade, it becomes calcium sulfate hemihydrate. This calcium sulfate hemihydrate is what we call as plaster of Paris. In common language, it is called POP. This POP is a white powder and it mixes with water to give a suspension. And it is, when it is put into or as a cast, and if it is again made into an aqueous suspension, it will reabsorb the water, and when it dries it forms back your hard calcium sulfate, that is gypsum, and that is how the plaster is cast, and it becomes very strong like a cement and stays on for a very, very, very long time. Now, we know, we have seen the use of plaster of Paris, of course, not only during the treatment of fractures, but also we have seen this in false ceilings. See, if you have a home which needs to be air conditioned, Invariably, every house has a ceiling which is more than 12 feet in height. So if you install an air conditioner there, and if you try to, you know, circulate cold air through the room, the air conditioner will have to work more, and there'll be a lot of expensive energy. So what they do is they reduce the volume of the room by putting a false ceiling. You've seen this in cinema theaters as well. A number of false ceilings are, incorporated into the hall, and this will reduce the volume. It will decrease the volume of the room so that air can be circulated more effectively. So plaster of Paris is used for making toys. Of course, you've seen a number of toys, especially you go to village fairs, you can see, or even any tourist place, you have peculiar shaped toys which are strangely colored, and once the color wears off, you find a white solid there. It is used for making decorative items and false ceilings and so on and so forth. So friends, with this we come to a fairly laborious topic, end of the topic, where we have discussed a lot about acids. We have seen what are acids, we have seen what are bases, we have seen salts, we've seen the preparations, we've seen the uses of a number of these substances. And of course, this is not the end of it. There is a large amount of information that is still available for us that is right now beyond the purview of what we are discussing. All right. Now, we'll just take a half a second breather. Breathe in, breathe out. Start with metals and non-metals. Well, the moment we hear the word metal, we are tempted to imagine certain things, like a metal is what you can see on your screen now. There is a metal here, the metal strap, and there is a non-metal here, which is the covering of the dial. There's a metal, and this is a typical non-metal. Then I have, yeah, here itself. Like if I remove this, I can't see you. In spite of it, will make an effort. This is your metallic part. The frame part of it is your metallic part. The plastic part of it is your non-metallic part. And the lens that I have there is made again of plastic, which is again non-metal. So we get some ideas about what are metals and what are non-metals when you hear them, because we're used to hearing these words quite often. Then, therefore, what are metals? To know what are metals, we'll perform a small, tiny activity. You can do this at home wherever you have some availability. Collect a few pieces of iron, maybe copper, easily available. Magnesium, not very easily available. Sodium, definitely not available at home. And we'll talk about sodium a little later. Then lead, yeah, lead also you might get it, yes. Zinc, yes, you will get zinc. You can easily find zinc in your home. I'll tell you where. Now, take a, you know, abrasive cloth, that is your sandpaper or yeah, sandpaper as you call it, or emery paper. Just rub it on the metal, you find that the metal shines. So metals have what is called metallic luster. Luster, lustrousness is a property inherent of all metals. I was mentioning about the sodium. Sodium is such a reactive metal, such a violently reactive metal. It is always kept under kerosene. And if you get to see sodium by any chance, it's a beautiful silvery white metal. Looks very lovely, very, very alluring. Don't ever try to touch it with your bare fingers, because you will have burns on your fingers, very serious burns. So sodium is a very soft silvery white metal, which is always encased in a lot of wax, and then it is kept submerged in kerosene for all the time, because if it is exposed even slightly to atmosphere, it undergoes rapid oxidation into sodium hydroxide, later on sodium bicarbonate, sodium carbonate, and so on and so forth. It becomes a mess at the end of it. So coming back to the metals that we can normally use and get to use, iron, yes, we can see iron. You can just take a emery paper, rub on metal iron piece if you have, it will start shining. Copper, yes, it shines, and you can make it more shiny by putting the abrasion on that. Magnesium, well, it is difficult to get magnesium to be seen at home. In case you get some magnesium pieces in your lab when you go to your school bag, you can always ask your teacher to give you a small strip of magnesium. In presence of the teacher, try to scrape the surface using a small piece of emery. It will shine. So metals have this shining or lustrous nature. In fact, the most beautiful of all metals, which you really want to see as a luster, is mercury that you find in a thermometer. And of course, today with the advent of the so-called heat sensing thermometers, this concept is going, but still, even now, the conventional thermometer with that beautiful silvery liquid inside the bulb, it is still uh, it is used by many physicians even now. All right. So when it comes to metals, metals are generally hard. They're usually hard. They are what we call as malleable, and they're also what we call as ductile. We will see what these are. Any metal can be beaten into a thin sheet. As young children, we used to do this because now it is not possible. Uh, so many restrictions in place, but as we were very adventurous in our younger days, where I lived, near probably half a kilometer from my house, we had a railway track running. And as small children, we would go near the track, keep one small coin over the track, wait for the train to pass over it. Crazy kind of ideas we had during those days. After the train passed by, if you are lucky enough to find the coin somewhere there, it would have become highly flattened into a thin, circle. So metals, and of course, you can try that at home. Take a old coin which is not in use, like a 25 paise coin, no more in circulation. Take a hammer and keep on beating over it. If you keep on beating, it will become thinner and thinner and thinner. This property is what we call as malleability. And if you go to a goldsmith shop, any goldsmith shop, you can see that the person makes a small ingot of gold. He melts it out in a crucible and takes it out and puts it into a small die and starts pulling it. When he starts pulling it, he starts getting a wire. Initially a thick wire into a smaller hole, thinner wire, into a smaller hole, a thinner wire. Like this, he can keep on making this wire and this metal into a wire. This property is called ductility. So metals are lustrous, metals are malleable, metals are ductile. One more. When I take a metal and hit it with any hard substance, I will find that it produces a nice sound. This property is called sonorous nature of metals. All metals are sonorous. Sonorous means making a pleasant smell, pleasant sound. Sorry, my slip of the tongue. This property is used to make bells. In fact, talking about bells, one information. The largest bell in the world, I'm told, is in Russia. Ages ago, I had seen a photograph of this. The bell is so huge that 50 people can stand below the bell. It's hung in air, and 50 people, full-grown males and adults, can, stand underneath that bell. It's supposed to be as huge as that, but it has never been gonged, and nobody has gonged the bell so far. Obvious reasons. Just it's an information, a small snippet here and there. So metals are lustrous, metals are malleable, metals are ductile, and metals are sonorous. Now, metals are also conductors of heat and electricity. How do we know this? Thermal conductivity, as we call it. What we can do is, a small experiment has been given to you in your textbook. It's a part of the textual exercise. You can try this. Fix a piece of a metal to a stand and see that this is coated with some wax, beeswax, and stick a pin to this, a metallic pin, a small metallic pin. If you stick to this, this end is free, only this part is wax, and this is your pin. You start heating at the other end. When you start hitting this at the other end, you will find that gradually the pin which was stuck to the wax will fall down because the wax melts. This shows that metals do conduct heat. Why such a complicated experiment? I don't think that it needs such a warrant of such a high magnitude. I'll tell you, make a small experiment on your own. Go to your kitchen. Anyway, your gas stove can be switched on any moment. Take a spoon with a long handle. Just keep it in the flame for a few seconds, and suddenly you find the free end of the spoon becomes very hot. Very simple. You are heating it at one end and you are getting the heat at the other end. That means heat is being conducted through the metal. So metals are good conductors of heat. Metals are also good conductors of electricity. We all know, because but for that, I would not be sitting in front of you, because my laptop is connected to a power source, and of course, although it has a battery, it still needs to be connected to a constant source of current. So the wire that is connected between the laptop and the power source is made up of a metal. So friends, with this, I guess we can more or less, another 3 minutes I have, I'll finish off the 3 more minutes usefully, and then we shall take a break. Now there's this experiment that is given to you again in your text. It's a very simple experiment. What he says is, make a circuit to happen like this, as it is now being shown. A battery, you can have a battery connected. This you can connect it yourself, you can do it at home. Connect this to a clip called A. Keep another here wire connected to the other end of the battery. Put a bulb there, electric bulb. Put a switch over there. Connect this to the other clip, or B. Now at this point, because they're away from each other, there will be no current that is passing through, so the bulb will not glow. Now in between the two, keep a conducting material like a metal. Keep a metal piece in between the two clips so that the clip is touching, both the clips are touching the metal. Suddenly you find that the bulb begins to glow. So when these two are connected by means of a metal, the metal helps in conducting of the current so that the bulb begins to glow. This shows that metals do conduct electricity as well. So we have some properties listed out. Number one, metals are lustrous, metals are malleable, ductile, sonorous. Almost all the metals are hard, excepting the alkali metals like sodium, potassium, lithium, and some of the alkali earth metals like calcium, and some metals like aluminum, which is fairly soft, lead, which is fairly soft, and mercury, a liquid metal. So, excepting for these small exceptions, all other metals are usually hard. They're quite strong, they're hard, they have high tensile strength. We'll be looking at this word much later, tensile strength. They are good conductors of heat and electricity. They make pleasant sound when hit with. They're sonorous. So, my friends, at this juncture, we'll be winding up. If you have any questions, if they have come up on the chat box, I'll wait for the things to come up and then answer you. Otherwise, do as usually what I say, like, subscribe our channel, subscribe to it, and we will have more interactions. Thank you very much. Have a nice day.
Thanks a lot, Balaji sir.
Haji.
And I'm very happy that all our teachers are giving not only the academic, also the life skill along with all the lectures.
Wow.
I'm sure, I know experts like you will not even understand that you have shared so much of wisdom during the class.
Me? It's a joke.
Not at all, sir. Let me tell our viewers, you have taught them the chemistry, how to make soap and all.
Oh.
Also, you have told them the life skill, how not to get carried away by the advertisements.
Thank you.
By giving them the TFM, total fat moiety.
Haji.
So by telling that, you have also given them the life skill that why and how not to get carried away with the advertisements also.
Exactly.
So that is how the expertise come into picture, unknowingly sharing the life skills along with the academics.
Thank you so much.
That's up to you, sir.
Anji. Any questions? Any questions today?
Not yet, sir. Our viewers are watching it more in the off time. Probably they have the classes.
I know.
So thanks a lot, sir.
Thank you very much, madam. Thank you so much.
Okay,
Thank you.
Thanks a lot, viewers. Stay connected with us.